How's it going, guys? And in this video we're going to be talking about false discovery rates in Python. We're going to be looking at how you can create a formula using some functions in order to be more confident in your data science analysis of a bunch of p-values. And so the background here is that if you had a bunch of random p-values and you were comparing two identical groups, there will be instances in which you are committing those type 1 errors. So you're thinking that they are false positives. You're incorrectly rejecting the null hypothesis that there's no difference between those two groups. And so basically what the Benjamini Hochberg equation or formula does, and I'm hoping I'm pronouncing that right, is it basically takes the subset of p-values that you have and it's going to focus in on the subset that are falling within that range that you care about. And if everything goes well, it will result in you having a lot more confidence that the observations you've had or the p-values that you've had for which when you look at the adjusted FDR p-value, you can be a lot more confident that you're not committing a false positive error. And so that is the key thing to understand about this. And to really hit home the theory, what I'm going to do here is just walk through how this works. And so what I've done is I've imported the random library in Python. And so what this is going to do is it's going to generate a list of p-values. And so I've got that here. And so basically if we look through this list of p-values that are just random numbers, but if you did enough statistical analyses, you're going to end up with a bunch of p-values. And so right now as we look through this thing, we're just seeing that every once in a while, like right here, we have a p-value that's really low. And that might lead us to think that maybe there was something statistically significant about that, but we don't know yet. So that's where we're going to come in here and apply the FDR adjustment. And so every time you run this, it's generating a new list of just random values between 0 and 1. And so the first thing you do when you are doing the FDR adjustment is you're going to sort the list of p-values you have in ascending order. So it means your smallest one is going to be up top, your greatest one is going to be at the bottom. And so the next thing you do is you assign a rank to each one of these. So rank will start at 1, not 0. We're not 0 indexed. And the other thing that's going to be important is to keep track of the number of p-values in your p-value list that you're going to be looking to, because the actual formula here for the FDR adjusted p-value is as follows. So you basically take the unadjusted p-value, so like in this case 0.463, and you're going to multiply this by the length of the p-value list that you're adjusting for, and then you're going to divide that by the rank of that item. So wherever that falls in that list, it'll probably be kind of near the middle, because that's a number that's in between 0 and 1 roughly, is something that we'll see. So basically, to reiterate here, I am creating a list of 1,000 random numbers between 0 and 1, and these would be something like your p-values in your experiments, and this is going to have a homogeneous distribution if you were to plot a histogram of this data. And then we're going to iterate through, and it's just a simple for loop here. And what we end up with, what I do to just show us the comparison, is I take the p-value, the unadjusted p-value, and I also take and I pair that to the FDR adjusted p-value in this dictionary. And so I append this into the p-adjusted list, and this is a list of dictionaries. And then once we run this code all the way through, we can see what happens here. So again, generating all that random p-values, and what we're going to see is that when we look in our p-adjusted list, we have really fantastic results. And this is the reason why this is such a powerful tool in our analysis, is because you can see here that even though our unadjusted p-value was ridiculously low, 0.0005, that would make us think, yeah, we can reject the null hypothesis. There's something statistically significant here. But when we look at the overall distribution of all of our p-values for this data set, and we calculated the FDR adjusted p-value, that ends up being 0.54. So 54% chance of it being a type 1 error. So that is why this thing is so powerful, is that because the original data set, even though it had a subset of p-values that landed within that region, existed, when you actually correct for them, you realize that your data set, because it was homogeneous, there really was no type of statistically significant distribution of p-values. And so this is doing exactly what we expected to see, which is we're getting adjusted p-values that are way bigger than 0.05. So what we're really seeing here is that we don't have anything to really report on. And so that's really good because it's agreeing with our null hypothesis, because after all, this is all coming from the random library. And so it's very unlikely that you will see any FDR adjusted p-value have a number less than 0.05. So I'm going to wrap things up with that. I'm going to provide a link in the description where you guys can download this. I hope this is helpful. Let me know if you have any questions. Talk to you guys next time.